let's discuss overloading. So we have discussed parametric polymorphism, and to recap, what parametric polymorphism gives you is you can use the same implementation in as many contexts as possible. Right? So you have a piece of code and it naturally works in exactly the same way uniformly across all sorts of different choices of types. So you can replace that choice of a type with a type variable, and there you go, essentially. Right? In contrast, overloading is a little bit different, because at its core, the idea is that the implementation of overloaded functions for different types is different. But you can still use the same function name. So one important aspect of overloading is just about reusing names, so that, for example, we have different implementations of what it means for two values to be equal for, say, integers or strings. Right? Nevertheless, we can use the same equality test operation in both contexts and don't have to remember new names. Right? But built on this core of functions that reuse the same name, there are again other functions that use these functions that have different implementations on different types, and they can then all be defined uniformly. If you recall all the way back, one of our first examples of functions in Haskell was the element function that checks whether a certain element is contained in a list. And in order to define the element function, we do need to perform an equality check by abstracting the equality check into an interface that can be implemented in possibly different ways by different types. The element function that uses this interface can be implemented in the same way across all these different types. So overloading is different because at its core there are different implementations, and that also always means that the choice is limited. You cannot have different implementations for different types and then come up with implementations that work for all possible Haskell types. There is always a limit with overloading, whereas with parametric polymorphism the choice is unconstrained. But by identifying common interfaces and possibly implementing them in different names, we still get that a whole lot of other functions can be implemented in terms of these common interfaces. At the core of overloading, there is the concept of a type class in Haskell. And the type class defines an interface that can be implemented by potentially many different types. Type classes are not themselves types. Type classes classify types. So EQ here on this slide is an example of a type class. EQ is the name of a type class. A new type class is introduced by this class keyword. And type classes always have a parameter, and that is a type. And so the statement EQ and then a type says that the type is an instance of the type class, that the type is supposed to implement this interface. So if we say EQ int, then this means something like int is an instance of EQ. Right? And basically what this class declaration now says is that a type A is an instance of EQ if it implements this interface. And so a class then is followed by this where word and then a number of type signatures that are indented with respect to the class declaration, all start at the same column. And these type signatures, they define the interface. There are no implementations in the class itself. The class defines the interface. When we actually say that a certain type is a member of this class, is an instance of this class, then we give the implementations. So there are corresponding instance declarations corresponding to these class declarations. There are instance declarations that we can give for concrete types, such as integers, booleans, lists. And with the help of these instance declarations, we can explain how a certain type implements the interface. Let's look at this in the editor. So of course the equality class is one of the most important classes that is provided in Haskell already, so it is part of the prelude. But we're going to do our usual trick and define our own version, so we have to hide it from the prelude. In this case, we learn a slightly new notation where we write EQ and then a parenthesis open and dot dot parenthesis closed. That is because a class is always, to a certain extent, a unit with the methods, with the functions or constants that are defined within the class. And in this case, we basically want to hide EQ and equals and not equals so that we can redefine all of them ourselves. And this notation basically says hide EQ together with all its methods. And then we can give a new definition of EQ here, class EQA, where, and we can start by first just giving the equality signature. Actually, it is a little bit strange that inequality is defined as part of the EQ class, but that is how it is done in Haskell. I'll get back to this. So far now we have a class with one method. If I now want to make a particular type an instance of EQ, then I have to use an instance declaration. Int is a good example in principle, but actually equality for int is relatively difficult to define, so we would rely on some built-in equality. It's much easier to define equality for a data type such as Bool. Right? Because for Bool we can just use pattern matching. So in an instance declaration, it starts with instance, the class name, and now the concrete type I want to make an instance of the equality class, right? And then where in the class declaration I have been given the type signatures, here now I have to give the implementations. So at the moment this EQ bool is underlined in yellow because I have not given an implementation of equals, and that is a warning, right? But now I can do this, and now because I'm supposed to give an implementation of in an instance for equality bool, I have to write a function bool to bool to bool, so I can pattern match on the arguments. And actually I can write equals in infix notation. So in this case, I'm actually going to appeal to intuition and say that it is most useful to consider the cases where both arguments are belonging to the same constructor, right? Where both arguments are true or both arguments are false, and then to consider any other combination. Namely, if both arguments are true, then they're equal to each other. So the result of equality is true. If both arguments are false, then they're also equal to each other, and the result is true. And in any other combination, if one of the arguments is true and the other is false, then the result is false. Okay, that is a good definition of equality. I can do some alignment if I want. It's optional as usual. And that's a good definition. We can give a similar definition for other enumeration types. Remember we had this choice data type in the beginning. Rock, paper, scissors. That had 3 options. We can give an equality definition for choice in basically the same way. You can say if we have rock twice, then these are equal to each other. If we have paper twice, then these are equal to each other. And if we have scissors twice, then these are equal to each other. And in any other combination, they're not equal to each other. Okay? Now, if we load this, we can actually also use it, right? So I can write paper equals rock, and I get false. I write paper equals paper, and I get true. And if I ask for the type of the equality method, right, I get one of these constrained types. So the types that come from a type class definition, if looked at on the outside, they always get the constraint that an instance for the corresponding type class must exist. Right? And if we start using this function in another function, then these other functions get these constraints as well. We have been doing that all the time already, right? We have been using functions such as the equality test and other functions. So that's not so unusual. So now we have an instance for equality and for choice. We may also want to give an instance for lists. So we could think as an approach that certainly is not very satisfactory if we have to start give an instance for lists of integers, for lists of booleans, for lists of characters, for lists of choices, and so on. We would like to give one instance for lists. But can we just give an instance for lists of A's, where the element type does not matter? We can try to do that, okay? Then we have to give an instance for an implementation for the equality function that takes two lists of A's and returns a Boolean. Okay. So again, we are following this pattern here where we consider situations where the constructors are the same. So if we have two occurrences of the empty list, then they are equal. And if we have two occurrences of cons, then we have to consider what to do. And if we have a combination where one argument is the empty list and the other argument is cons, then they're almost certainly not empty. So that's a good starting point. All right. So line these again to make it a bit clearer. So now we're still kind of writing a function over lists, so we probably want to do a recursive call here. And a recursive call on the equality of x's and y's is fine, because we are just defining the equality on lists, and that can of course be recursive in Haskell. But we also have to do something with x and y, and in fact for these two lists to be equal, x should be equal to y, right? And xs should be equal to ys recursively. So that is really what we would like to write here. X equal to y and xs equal to ys. Now x equals to y, though, is at a different type. xs equals ys is at the type list of A, and we are just defining an instance for list of A's. But x equals y is at type A. Y is of type A, as we can see here. X is of type A. And indeed, we get an error message that says no instance for EQA arising from a use of equals equals. Because we have claimed here that we can define an instance for equality for list of A where there is no constraint on the A. But in fact, we can only really give an instance for the equality of lists of A's if A is already an instance of equality. And the instance declaration syntax allows us to write something like this. We can say this by putting a constraint here into the instance declaration, we can say exactly this. We can say, we can give an instance for equality of list of A, but under the condition that there is an instance for equality of A. Right? And with this, the definition type checks, and you can see that if I now have a list paper, rock, paper, and I compare this with another list paper, rock, paper, then it actually works. If I change the list in one way or the other, then it returns correctly false. So this works, and we can also compare lists of booleans, and we can also compare lists of lists, right? Because we have a list of choices is now an instance of equality, and then a list of choices is also an instance of equality. Yeah, I mean, let's just take the same so that we can see. Oops, sorry. Oh, that didn't go well. A list of choices also works. Okay. But for example, in our equality class, this is still our own, not the one that is predefined. Integers are not currently an instance. So if I have an integer or any number, actually, this will lead to a type error because we don't have the right instance. And so a list of numbers can also not be compared for equality because we currently don't have an instance for equality of numbers, right? So in order to compare two lists, we have to have an equality instance on the element type. But otherwise, it is pretty straightforward. It is a good moment, actually, to also introduce a language extension, another language extension, because one of the strange aspects of the Haskell language standardized is that it is not allowed to give a type signature for a function that occurs within an instance. It may be enlightening here, actually, to write that in this case, that we are defining the equality instance for booleans, the equality function that we're defining has to have the type bool to bool to bool. That is the case, right? That comes from it. But syntactically, Haskell does not allow us to do this, but it actually hints at the fact that we can use a language extension that is called InstanceSigs, for instance signatures, to enable this feature. And I think it's good to briefly mention this. So if we, again, at the beginning of the module, similar to how we did for bang patterns, add this language extension InstanceSigs, then this type signature for the instance is allowed. And then similarly, we could write here that in the case of choice, the equality function has to have the type choice to bool. And in the case of lists, it has to have the type list of A to list of A to bool. We don't have to repeat the EQA constraint here because that is already global to the instance. We have that in scope at this point. Similarly to how we don't have to repeat the EQA constraint here for the equality function in the class definition itself. Okay. Now, as I said, the actual definition of the equality class actually has two methods. It has equals and not equals. So it has a second one. And then, of course, we get all our instance declarations that we've written so far underlined again with warnings, because they now all say that we don't have an explicit implementation for not equals. And if we don't have this, then it would crash, right? I mean, so that's not good. I mean, it's good that it's at least a warning. So if we compare true unequals false, we now get a crash that actually says that there is no instance or default method for class operation not equals. And of course, one option would be to, and that's actually what I probably would have done, is to take not equals out of the class and to just say this definition has the type EQA double arrow A to bool. And how is it defined? Well, if we want to check whether x is not equal to y, we simply check whether not of x equals y holds. And that is one option to do this in general. What Haskell does instead is it does move this definition into the class, but in order to prevent us from having to give definitions of all the class methods everywhere, like both equals and not equals, in a rather tiresome way, right? Writing a lot of redundant code. Haskell has this concept of default implementation, so that deviates from the rule at the beginning that I said in principle classes have only type signatures and no implementations. You are allowed to give implementations in classes themselves, and then they are default implementations. And if you omit the definition of a function that has a default implementation, then the default implementation is taken, and we can also see that the warnings disappear because there is now a default implementation. But we could still give an explicit implementation of not equals that would deviate from the default definition. In fact, the equality class in Haskell goes even further. It gives a default implementation for equals as well, in saying that the default implementation for equals is that is the negation of not equals. And that would allow us to provide an implementation of not equals only, rather than, right? So now we basically can choose to implement one of the two functions. We can either implement equals and use the default for the other, or we can implement not equals and use the default for the other, or we can actually still explicitly define both. But with this mutually recursive default, there is a problem or a danger, namely that if we forget to write any definition, that's like for the choice function, let's just comment out our definition, just put it into comments. Then we don't get a warning now, because both definitions have defaults. And if we start calling rock equals rock now, we get a loop. So that's not so great, right? Because the equality default implementation calls the not equality default implementation, and the not equality default implementation calls the equality default implementation, and so on and so on. So that's a bit dangerous, that we can now forget giving these implementations and not even get a warning. That is why there is an additional construct in the Haskell language that is a so-called minimal pragma. At least that is a construct that is supported by GHC. And the minimal pragma allows us to specify what the minimal amount of functions that you're supposed to define are. And we have to do that separately, unfortunately. But we then at least get our warnings back. And the syntax for this is a little bit ad hoc, but essentially you can read this as an OR again. And in this notation, the minimal pragma essentially says that we have to give an explicit definition of at least equals or not equals. If we omit both of them, then it's not okay. And you see that now my problems counter went up to 1 again, and now suddenly I have a warning back for EQ choice that says, translating the minimal pragma, that there is no explicit implementation for either equals or not equals. And this comes from exactly the minimal pragma. And if I remove the comments from this definition, then my warning disappears and everything is fine again. We can use the :i, the info command, on classes as well in Haskell. And I think if I do this now, I'll, well, actually it does still give me the one. No, it does give me the one that I've just defined. It tells me here, define that overloading 6.1, because I've hidden the one from the prelude, right? So now let's actually have a look at the prelude defined one. So I'm going to restart GHCi without anything loaded. So I'm in the normal prelude context, and I'm saying :i eq here. And we see that there are lots more instances in scope. So actually, this is an interesting thing to look at. So when we looked at it before, we got our own definition of EQ. We see our two methods. It actually also includes the minimal pragma. And then it lists the instances that we have in scope. You can ignore this safe annotation for the time being. That is irrelevant at the moment. And you can see we had these 3 instances. It does not give the definitions. It essentially just lists for which types you can assume that you have an implementation of the equality interface available. So similarly, if we do this in the prelude context, we get the class declaration, and you see that it looks exactly the same, including the minimal pragma. It does have a minimal pragma just as the one that we have defined, but it is defined originally in a very different module. And you can see that the instance for lists that we had defined exists in exactly the same way. But now we also have, for example, an instance for integers, we have an instance for doubles, we have an instance for characters, and we have the instance for booleans, which is also in principle defined in the same way as we have. And then there is usually a lot of noise, and this is coming from tuples, because tuples are all different data types in Haskell. A pair is a different data type than a triple, and so this takes a lot of space. So there is, for example, this one is relatively readable still. There is an instance for pairs that says you can compare a pair of A and B for equality if there are equality instances for both the A and the B type. So this here is a pair of constraints, so to speak. So these are 2 constraints. This is not really a pair data structure. If you have multiple constraints, we have seen this before in other examples, then they are just grouped together to the left of the double arrow in a tuple-like syntax. So this basically just says if there is an equality instance for A and there is an equality instance for B, then we can also compare a pair of an A and a B for equality. And similarly, we have one for triples and we have one for quadruples. And actually, interestingly, this stops. So there is a maximum size. I think it is 16 or something like that. So if we start comparing tuples that are going beyond a particular size, they're no longer comparable for equality. So let's just try this out once for the fun of it. Right. This is a tuple with 16 components, and we see if we try to test this for equality, it'll say that there's no instance, even though we're now in a prelude context. If I go back by 1 component to 15, then they can still be compared for equality. So this is actually one more reason, if there hadn't already been enough reasons, to simply try to avoid, if at all possible, tuples that have this size. Use user-defined data types of a particular size for which you can then give an equality instance manually. And the deriving construct, I'll get back to that we have already seen in action for the show class in particular, that also works for the equality class. So you don't actually end up having to write your equality instances by hand. But yeah, so there is a limit to the predefined instances for tuples. And then what do we have left? We have one for the unit type. We briefly mentioned the unit type a couple of times. It's sort of a nullary tuple, if you like. So a data type that has only one value, which is also written like this. And that type can trivially be tested for equality. Unit is equal to itself. There are no other values. We'll see that this unit type plays a bigger role once we get talking about I/O. And then there is an instance for maybe, which again requires an instance for the element type. And there is an instance for either as well, like the type that is a choice between either being an A or a B. And again, in the general case, in order to compare to either values for equality, we need both an equality instance for A and an equality instance for B. So there are quite a few in scope, and these are just the ones that are basically in scope if you are in a prelude context. There are more equality instances defined for other data types and other modules, but you have to import these modules in order to get access to these instances. The :I command will not just show any instance defined anywhere, right? It's not, it cannot predict the future, so to speak. That's a good introduction to sort of the basic syntax for introducing classes. Let's just, before we end, say that this is actually something that you're going to do relatively rarely in Haskell. You rarely define your own classes. I mean, it does happen, but it is not a common thing to do. The reason is that classes in Haskell are being used to describe common, widely used interfaces, such as a data type supporting an equality test. Most of the common, widely used interfaces are known. They are in existence already. These classes are defined in the library somewhere. So what you typically do when you're writing your own Haskell programs is you define new domain-specific data types, and you may choose to make these new domain-specific data types instances of already existing classes. Sometimes, but much, much more rarely, you're also defining new domain-specific type classes that give interfaces that are meaningful in the context of your application, but for a variety of different data types. But that is much less common, right? So typically defining new functions, making them instances of existing type classes, defining new data types, making them instances of existing type classes, and defining functions that operate over your new data types. Those are the common ingredients of writing Haskell code. So next we're going to look at the most common interfaces, the most common type classes that you will have to deal with. With equality, we've now already discussed one of them to quite some extent, but we're going to look at several others, and while we are discussing them, we'll also see some additional aspects of the mechanisms, like of defining classes and instances. But mostly we have covered the important aspects now already. So the rest is mostly just building vocabulary, getting familiar with what the most common type classes are and what kind of instances you can expect for them.